Good morning, everybody. Today we have Martin López-Corredoira. Martin did his PhD in physics in La Laguna, and then a bit later in philosophy in the University of Sevilla. He was abroad for several postdocs, and then he moved back to La Laguna, where since 2011 he's a staff researcher here at the IJC. He works on several fields, including the morphology and dynamics of the Milky Way, large-scale structures, and also on quasars, which is what he's going to talk about today. Thank you, Martin.
Hello. Yeah, it's working. So today I will speak about two different topics related to quasars and the problematic and the problems to understand these kinds of objects. So I will give two short presentations of 15 or 20 minutes of these different topics, and in the end I will also mention other problems which are in the literature about quasars, which show some kinds of controversy or some kinds of difficulties to understand these objects. So the first one is this one about the evolution of the masses of black holes. It is well known since many years ago that there are many very bright quasars at high redshift. Very bright, I mean absolute magnitude of up to -30 or even more, -32, which is 10,000 times the luminosity of the Milky Way. And these kinds of objects which are at high redshift are totally absent at low redshift. There is no at all very bright quasars at low redshift. For instance, if you go to the Sloan and you try to find quasars with luminosity higher than the equivalent of absolute magnitude -26, which is not too much, it's -26, there is no one for redshift lower than 0.4. This is indicated in these diagrams, in which they show for different wavelengths in X-ray and also in visible how there is a high co-moving density of faint quasars at low redshift, but however there is a very low or totally absent, because here there are no points in this here we have no statistics because there is no quasars. There are a totally absent of very bright quasars at low redshift. So we can ask which is the reason for that. There are two kinds of explanations. Either we have to admit that there are no very massive black holes at low redshift, or if there are very massive black holes, very massive, I mean masses of 10 up to 9 or 10 up to 10 solar masses. If there are these kinds of objects, they should be with a very low efficiency. The Eddington ratio should be very low to produce a low luminosity. Which kinds of answer is the correct one? For that, we have to investigate the evolution of the masses of black holes as a function of luminosity for different redshifts. There are several methods to derive the masses of the black holes associated to quasars. For instance, in the paper by Shen et al., they use the spectra of Sloan, and they use different lines. For instance, the H-beta line, the magnesium 2, and the carbono 4, depending on the redshift of the quasar. For high redshift, they use the carbono 4, for instance, and for low redshift, they use the H-beta. There are some small differences in the calibration of the masses of the black hole, depending on the different estimators, but they are not so important for the question I want to speak about. In the end, you can get a plot like this. These are the masses of the black holes of the spectroscopical quasars for the Sloan up to the 2008. Nowadays there are more quasars because we have the Sloan 3. But we can reach redshift 4 or 5, the maximum redshift here. And we can see very clearly that the very massive objects are all of them at high redshift, and there are none here. We may wonder whether there is some selection effect, and effectively there is a selection effect. There is a Marquardt bias very clearly. At very high redshift, you can only see the very luminous objects, and the very luminous quasars are associated to very massive objects. So in order to separate both effects, depending on the luminosity and the redshift, we can plot the masses of the black holes as a function of both variables, of the redshift in one side and the luminosity, or what is the same, the absolute magnitude. And what we can see here is that there is a very clear dependence here. Of course, the masses are indicated with different colors. There is a very strong change in color in the horizontal axis, in the direction of the horizontal axis, which means luminosity. However, if you fix the luminosity, the variation in the vertical direction is negligible. So there is no change of masses for a fixed luminosity with the redshift. Or, what is the same, there is no evolution. This dependence of the mass can be fitted approximately very well with a double linear fit, like this. Here I plot the residuals, which are relatively low compared with the values obtained before. And we can see that in this double linear fit, the dependence with the redshift is very low, almost negligible compared with the error bars. However, the dependence with the luminosity is quite significant. It's the most important in this. Of course, I'm talking here statistically, that there may be some deviations for some particular objects, but in average, we can say that the masses of the black holes depend almost only on the absolute magnitude, not on the redshift. Magnitude, yes, this is the magnitude, absolute magnitude in the I band, in the I filter of the quasar. Of the quasar, yes, of the quasar, which is related also with other magnitudes and with the bolometric luminosity. You can relate it, but this is the absolute with K corrections. With K corrections. The same thing happens with the Eddington ratio. In this, it is related with the mass, of course. We should expect the same dependence. If we plot the Eddington ratio of the quasars versus the redshift and the absolute magnitude, we see that the dependence with the luminosity is quite strong, as expected, but the dependence with redshift is almost negligible. Here we have a very small factor which is compatible with zero within the error bars. And the residuals are these of the fit, which are low too. So in average, up to redshift between 0 and 5, we can derive something, a very simple law like this, and this law, this dependence of the mass with the bolometric luminosity is almost independent of the redshift. There are some uncertainties in this calculation. For instance, in the estimator of the masses, depending on the estimator, there are uncertainties of 0.1 or 0.2 dex. Also, to estimate the bolometric luminosity from the visible filters, there are different methods, and they have some uncertainties too of the same order, or the possible intergalactic extinction, etc. But these are, compared with the variations we want to measure, these are not so important. So the conclusion is quite robust. We can say that the evolution is compatible with zero, no evolution at all, or if there is an evolution, it is very small, it's very low, the change of the masses with the redshift for a given luminosity. This has several implications. First, if we accept the standard picture of why the black holes in the quasars emit such a radiation, in which the standard picture offers says that there is an accretion of matter onto these black holes, and this is what powers the stream luminosities of the quasars. If we accept this picture, and since we say that for a given mass, the luminosity is the same, for any redshift, we must conclude that there is not a very significant change in the conditions of the powering of the fueling of the quasars. The accretion rate should not be. There may be some small difference, but not so important, because if there were very important differences, we should have much higher luminosity for a given mass, and we don't observe this. If instead of the accretion, we think that the powering of the quasars is due to the mergers or the star formation, we should conclude the same thing, that the conditions, the environment conditions of the black holes are not changing strongly, but we don't detect this strong change. There are also other signs in the literature of changes of no changes of quasars. For instance, it is not observed any evolution in X-ray properties for quasars up to redshift 6. Also, the spectral features of quasars invisible are quite similar. Even the metallicities and other things which are observed in quasars are not so different. The host galaxy mass is proportional to the black hole mass, and this proportionality is also quite more or less independent of the redshift. So there are several signs of which point that we don't observe any evolution in the conditions of the quasars. Of course, I mean, once the black hole was formed, it is evident that we observe something different at high redshift, at low redshift. At high redshift, we observe very massive objects, and at low redshift, we don't observe them. But I don't speak about this difference. I speak that once you have your black hole of 10 up to 8, 9, 10 solar masses, once you have this black hole, the behavior is quite similar at low redshift and at high redshift. The second implication is related to the question that I have asked at the beginning. When we ask what happens with the local quasars, why there are no very high luminosity quasars at low redshift? And the answer is because there are no high mass black holes at low redshift. There is an absence here of very massive objects. Very massive black holes, I mean, in the center. Yes. Yes, active black hole, of course, yes, sure. I mean, I'm talking about quasars, always, the activity. Of course, they may be in other galaxies. This is something I mentioned later. You mean that if the volume is enough to... No, it is not. It is not. Yeah, but this is implicit. This is implicit in the analysis in which I have separated the redshift and the luminosity. Of course, for instance, if you go to this plot, the first one, certainly at high redshift, you don't have the faint objects, is what you mean, of course. But you have the very bright objects. For instance, at high redshift, you can analyze the object with magnitude minus 28. They are only observable at redshift larger than 1. But here, between 1 and 4, you don't observe any evolution. At low redshift, it is the opposite. You don't observe any bright object, which is the gap here, and you observe only the faint objects. But always looking in the vertical direction, fixing the luminosity, you don't observe a significant variation. So, answering your question, yes. Yes, sure. I agree. I'm talking about the quasars. This is something that I point in the next transparency. The Yes, I'm talking about that we don't observe any massive black holes in quasars. There may be massive black holes in normal galaxies, non-active galaxies. Yes. You mean at low redshift? Well, in this I have not carried out this calculation. This is implicit here in the first transparency that I have shown here. This is a paper by Hopkins in which they have calculated the bolometric luminosities, but also the luminosities in other wavelengths. And here you can see the statistics of the quasar. The bright, we know how many bright quasars, bright in apparent magnitudes are. For apparent magnitudes lower than 15, which I think is more or less the limit of Sloan, there may be 200 quasars in the whole sky. And these are in the catalogs of the... Yes, I understand, but they are, anyway, of course, you are talking about Sloan, maybe you miss this object, but you can see in other catalogs, other previous catalogs, in which there are no such objects. If you have, I don't remember the number, but if you have a very, imagine that you have an object with magnitude -30, which is observed indeed at high redshift, at point 1 or point, maybe the apparent magnitude should be 8 or 9 or lower than 10. There is no such an object. The brightest object we know is the 3C273, which is magnitude 12 or something like that. It's very, there is no problem with the bright objects. Maybe you have a problem with the faint objects at high redshift. And I admit that we don't have enough statistics of the faint object at high redshift because of the Markov bias. But with the bright objects, you can. They are available in other catalogs apart from the Sloan, so there is no problem with that. In these statistics, yes. This comes from Sloan, yes. No, there are. I have checked it. I have checked it with the net, for instance. If you go to the net, and the same thing. I have said at the beginning. There are no quasars brighter than -26 invisible for redshift lower than 0.4. This is true in the Sloan, but if you go to the net, it's also true. There are no quasars of such absolute magnitude. Here we have another work, for instance, Steinhardt and Elvis. They have also carried out some statistics of the co-moving density of quasars as a function of the masses of the black holes, and we have the same result in this. Here, in this color, the magenta color indicates the most massive quasar, black holes in quasars, I mean. And you see that here there is a gap. There are no at all. The statistic is finished because they have not detected anyone at all. If there were something, maybe the line should be over here, 2 or 3 points lower than -3. But of course, we have not enough statistics. In any case, it is clear that there is an absence of very bright quasars, which means very massive black holes, active, of course, as you say, in quasars. The point that you have remarked is totally true. We can make 2 questions about this. Where are now these very massive black holes? These black holes with 10 up to 10 solar masses. The standard explanation is that they are now in the center of inactive galaxies. This is the explanation, in the center of very massive galaxies, in the CD galaxies or other kinds of galaxies. And I have read some papers in the literature, and apparently there is an agreement of the statistics of these massive black holes with the missing black holes. However, this does not answer the question at all of why don't we have nowadays these quasars with very massive black holes. We know that the black holes have a finite life, and once they have finished their activity, they are in the center of non-active galaxies. But what happens with the triggering of the new quasars? Why don't we have triggering of very massive black holes nowadays? Why at redshift 1 or redshift 2 you can observe black holes in the center of quasars with 10 up to 9, 10 up to 10 solar masses, which are triggered by some conditions, and nowadays this does not happen? Why don't we have any new quasars? I don't mean the old black holes, but any creation of new black holes. And this is the answer, the question that, in my opinion, is not very clear, because taking into account all the elements that I have mentioned here, if there is no evolution in the relation between the masses and the luminosity of the black holes, in some sense, it means that the conditions of accretion, of merger, of star formation are not so different at that time. Even if you accept the standard hierarchical scenario with the major mergers and so on, if you accept that, you should observe more massive objects at lower redshift, because the merger is with smaller objects into a larger object, but we don't observe that. So still, there is something that I do not understand. Maybe some of you can give some discussion about this, but why don't we have now any triggering of new quasars with such a high mass? What happened in the past that is not happening now? This is the question. But you should observe also some evolution in such a case of in accretion. Yeah, yes, but not in this. Yes, no, I know there is transformation, but why there is no change then in the luminosity of the quasar for a given mass? If there is such a huge amount of gas which is accreted, you should have a higher Eddington ratio, and then there should be. Possibly, yes. The question, I do not give any answer. The question is that we have the problem that there are no. The problem is that we have very few. The problem is that we have none at all. And in a very short period of time, I mean from redshift 0.5 to here, the quasars of the very massive quasars have vanishes at all. So this is such a strong evolution in the conditions to trigger new quasars. As far as I could see, I have not seen any model to explain that, but maybe there is something. There are quasars with low but we are talking about 3 or 4 orders of magnitude lower. It looks logical, but then you should explain why the accretion, the efficiency, the Eddington ratio of the quasar of the black hole remains the same. Because if there is no gas, it should go lower the Eddington ratio. And we observe that the Eddington ratio for a given mass, if you have now for the low. The small black holes with lower masses, with 10 up to 7 or 10 up to 8, which are common in all the redshift, they accrete the same and they produce the same luminosity for all redshift. Why? If the conditions are so extremely different for... No. Now I am talking about, for instance, about... These are the bright objects, are this red one. But let's talk about, for instance, this -26, for instance, which are common. You can observe quasars with -26 at low redshift, relatively low redshift, and also at redshift 2. And you see no evolution of the masses for a given luminosity, or what is the same, no. So if there were such extreme differences in the amount of gas surrounding the quasar, you should observe first that the triggering of quasar is much more important at high redshift, but also that the efficiency is also much more important. And we don't see any sign of this evolution here. Normally, the host galaxies, the masses of the host galaxies is proportional to the masses of the black holes in the quasar, yes. So if you go to the most extreme, here you have very massive galaxies. Possibly, yes. Here is 10 to 10. Or maybe this is 10 to 12 or something like that. The problem is that we don't see the host galaxies at very high redshift. With the Hubble, you can reach maybe the redshift 1 or so to measure the properties of the host galaxies, but we cannot observe the host galaxies at here. But I think there is some work here by Mauricio Cisterna. I don't know whether he's here. Yes. In which you have analyze the dependence of the host, the masses of the host galaxies and the masses of the black holes, and they are directly proportional. No? And you reach up to redshift 0.9. It's safer in general. Yeah. A bit low. Yeah. Well, we go to the next topic, and in the end, if you want to continue the discussion, this was the first topic that I wanted to talk about. The second one is quite different, but it's also related to quasars. Is the question of the ejection, the jets in quasars, and the superluminal motions. There is a catalog which is now publicly available, which is the MOJAVE, in which there is a monitoring of the jets of AGN in general, but within this AGN there are a lot of quasars. And this is done in the radio, the 2 centimeters, with a very high resolution. So you can reach a resolution of few milliseconds, which is translated into a scale of few parsecs. Here I will show you some cases of monitoring of the jets, in which you have one main object, which is the center of the quasar or any gem in general, and you have some jets which are formed, and they are ejected. The separation between the center of the blob and the center of the quasar is being increased. With these separations and checking the evolution with time, you can measure the apparent velocity of these objects. And they have, in this catalog, there are some cases in which the apparent projected velocity in the tangential direction is as high as 60 times the speed of light. This is the most extreme case. Here I show you another one. This is an object which is somewhat closer. It's a redshift 0.5, and there are several blobs. And one can see how the blobs are being slightly separated from the center. With this separation, of course, you can calculate the velocity. Here is the epoch in which it is observed. There are plenty of objects like this in the MOJAVE catalog. They have, in the version up to 2009, they have 135 AGNs in general, and from these, almost 100 were quasars, so the luminosity is high enough to be considered a quasar. These 101 quasars produce in total 354 blobs ejected by the main body. And 95% of these blobs present superluminal motions. And also 45% apparent superluminal motion larger than 10 times the speed of light, which is quite high. There is an explanation for that. This is not a contradiction with the special relativity. We know since the 60s or the 70s that a relativistic jet pointing in the direction close to the line of sight can produce this effect. So if you have a relativistic jet with a small angle with respect to the line of sight, the apparent projected speed in the tangential direction can be much higher than the speed of light. And this is just, you can carry out the calculation with the equations of the special relativity, and there is no any contradiction with Einstein relativity. However, well, first I want to talk about another thing. However, there is apart from the fact that you have a very high velocities, you have also a very huge magnification of the flux of these blobs. This is what is called Doppler boosting. So at low angles, for very highly relativistic jets, you have a very high magnification of the flux of these objects. This, indeed, is it gives the explanation of the existence of this huge amount of superluminal motions in this catalog. There is a very important selection effect. The jets which are in the direction close to the line of sight are much more amplified, so you observe a much higher number of these jets than the jets which are in other directions. So this is the explanation why you observe so many objects close to the line of sight. So there is nothing anomalous here up to now. The topic that I want to speak about, however, is not any contradiction with the relativity or something which cannot be explained. The topic is that how much energy do you need in these jets to produce such a highly relativistic objects? This is the topic. We can calculate the kinetic power of these jets roughly, a rough calculation, just multiplying the frequency of the ejection of these blobs by the mass and the the Lorentz factor of associated to this ejection, the relativistic Lorentz factor. For the mass of the blob, we have to make some assumptions because it's not direct. We assume that the blobs emitting synchrotron radiation, and we assume the minimum energy assumption, that is, that the magnetic field and particle energy distributions are arranged in the most efficient way to produce the synchrotron emission. With this, and also making statistics about all possible values of the Lorentz factor. We don't know in principle the Lorentz factor, but we can calculate the probability of a Lorentz factor given that we observe such an apparent velocity. Doing some calculations that I will not specify here, we can estimate that the necessary kinetic power for each quasar is around 7 times 10 times to 47 Earths per second for each quasar, in average. This calculation depends on some parameters that we have used in the calculations. If we change the parameters, there is some variations. In most of the cases, this number is higher, or can be slightly lower, but the order of magnitude is more or less the same. So the minimum amount that we get here is something like 1 times 10 to 47 Earths per second. So this number in this is quite conservative, is what I mean. So most likely it will be larger, but not much smaller. There are also some uncertainties related to the calculations. For instance, we have for the calculation of the mass of the blobs, we have assumed that the plasma has the maximum limit of the 10 electrons per proton. In this, according to the literature, this number should be lower. 10 is the maximum number which is expected. So if the number is lower, since the mass of electron is here in the denominator, the mass of the blob could be even higher, but not lower. So again, we are being quite conservative in the calculation of the kinetic power. Also, other factors like the volume of the jet or the minimum energy assumption itself do not change significantly the order of magnitude of our calculation. Here we plot the kinetic power, the estimation of the kinetic power, because this is a rough calculation, for each of the quasars, of the 101 quasars, versus the luminosity in radio. There is a correlation, as expected, with a huge dispersion, but anyway, the correlation is significant. It's 3.5 sigma. So this means that the quasars with higher luminosity in radio present the higher kinetic power in general. There is a Marquin bias here, again, and here we cannot separate both effects, the luminosity and the redshift, because we have not enough number to do the statistics. So we have to bear in mind that the higher luminosities are observed also at higher redshift. In this plot, I show you also the kinetic power of some quasars in which we have information about the masses of black holes, quasars which were also observed invisible. There is also some correlation, although the correlation is not so significant here. The important thing is that the kinetic power is of the order of magnitude of the Eddington luminosity of the quasar. And the Eddington luminosity is some important portion or the order of magnitude of the bolometric luminosity. So we are talking here that the amount of energy ejected in the jets, in the form of jets, is of the same order of magnitude as the amount of energy in the bolometric releases in the form of photons. It's a very important amount. This is in agreement with some other works which are doing some calculations in the parsec scales, but however, other works, other references which talk about the calculation of the kinetic power in kiloparsec scales give a much lower number, 2 or 3 orders of magnitude lower. So the question here is, well, one answer is that some of these works is wrong. Either our work or other works are wrong. But assuming that everything is correct, the question is how this energy is dissipated, how this amount, a huge amount of 10 up to 47, 48 Earths per second in each quasar are ejected into the intergalactic space, and this energy is dissipated in some sense. Because at high scales, at scales of kiloparsec, there are no signs of this of the release of these huge amounts of energy releases. And these are indeed the conclusions of this part. First, we have the apparent anomaly that there is a huge amount of objects with a very high superluminal motions. Even half of them have apparent projection of the velocity 10 times the speed of light or larger. And this can be observed, of course, with the classical theory of the ejection in the line of sight, but with the condition that you need a very high Lorentz factor, very energetic ejection. And for this energy to be released, if you do the calculation of the kinetic power, you get the conclusion that the amount of energy released by the quasars in the form of this ejection is of the same order of magnitude as the bolometric luminosity. This is the important thing, which is in some sense in contradiction with what is observed at higher scales, at kiloparsec scales. So there is something here that we don't understand very well. So this was the second part. And just to finish, only 5 or 10 minutes, and then we can discuss something. I can mention other controversies, other problems which are in the literature, without giving details of these things. There is a classical example of controversy, which is the correlation between the low redshift galaxies and high redshift quasars. And this was very much discussed since many years ago, since 40 or 50 years ago, since the discovery of the quasars, and nowadays it is a forgotten topic almost. Indeed, I have been working 10 years ago, between 10 and 5 years ago, I have been working some details of this, and now I'm not working anymore. But there are still some things which are, in my opinion, not very clear. The question is that there are some correlations, cross-correlations between the catalogs of galaxies and quasars, and also there are some individual cases of objects which apparently, and this is the question, apparently present some connection between these kinds of objects. The orthodox reply says that in most of the cases, the surveys of quasars were incomplete. There was some bias, or these filaments may be artifacts or superposition of contours, or some problems with the reduction of the objects. There is an important explanation, and in this works very well for some of the cases of correlation, the gravitational lensing. Of course, maybe gravitational lensing can explain some of these correlations, because due to the gravitational lensing, you have more objects closer to the galaxies, and this produces a correlation. And as I say, this works for, as far as I know, for some of the statistics, but not for all of them. And also some other discussions about the nature of whether the probabilities are a posteriori or not, or these kinds of things. There is something also important to take into account, which is the correct identification of quasars. When you say that you have a correlation, you have a quasar near a galaxy, you have to be sure that this is really a quasar, of course. And in these cases, according to what I could see by my own analysis, this is not true. There are some cases in which these claims are not correct. I will give you just very briefly 2 examples in which I have been working. For instance, in the 2003, Barbies et al. Have claimed that there were an excess of X-ray sources near some nearby galaxies. And they said that most likely these X-ray sources should be quasars, background quasars, with different redshift. However, in some analyses that we have carried out together with other people, we could see that in more than 50% of these ultraluminous X-ray sources, more of the 50% were quasars, but there were other 40 or 50% in which they were not quasars. They were H2 regions or other kinds of objects. In this has given place to a new line of research, which is the research about intermediate X-ray objects. Are objects with black holes of few hundreds of solar masses. But for the question is that statistically there is, in most of the cases, there is not any anomaly here because these X-ray sources, in most of the cases, are not quasars. Only in few of them, like this, for instance, these two, we could see that they were in these quasars, and the probability to have these objects near the galaxies were very low, something that we could not understand. But for most of the cases, we could understand that this was a wrong identification of quasars. Also, the same thing with this catalog created by Flesch in the 2004, in which they gave a catalog of candidates for quasars based on photometry only, not spectroscopy. They have cross-correlated maps of radio, X-ray, and optical, just looking for blue point-like objects, and they have created a catalog with objects which most likely are quasars. We have carried out some follow-up of these objects and making spectroscopy of some of these candidates, and we could see that the probabilities were overestimated, so they were not right. There was not any anomaly here because in the objects they were saying that they are quasars near galaxies. Most of them were not quasars, were other kind of things, so there was no anomaly. This does not mean, as I say, that the problem of this anomalous redshift or correlation galaxy quasar is already solved. In my opinion, it's not totally solved. The question is that people is reluctant to make research in this kind of research. They don't want to know anything about this. They say they think they have the solution, so they don't want to do any research. And there are, in my opinion, some cases which are not understood. I don't say that they are in favor of any anomaly or not, but I mean that we don't understand some statistics of quasars which are near quasars, why they are so. So this is, in my opinion, one of the pending problems still to be solved. Other anomalies that I have found in the literature, which are, in my opinion, are interesting, is, for instance, this analysis by Genavi and Prochaska in the paper by 2007, in which they have used pairs of quasars, which are very close. The angular distance between these quasars is very low. And they could analyze the absorption lines in the pairs of quasars. So you could see the structure of the clouds in the radial direction of this quasar and also in the tangential direction of this quasar. What they have found doing the statistics with many pairs of quasars, not only one object, but many pairs, they have found that the structure in the transverse direction of the quasar is higher, the amount of structure is higher than in the radial direction, which is something which I don't understand, because in principle one should expect some isotropy of the distribution of clouds around the quasar, not to observe more clouds in the transverse direction than the radial direction. There is the problem of the periodicity in quasars, although this was much more discussed in the last years. Still, there is some people who find some statistics in favor of some periodicity of the redshift in quasars. There is an anomaly also of the absence of time dilation in quasars. Due to the expansion of the universe, one should expect that any period of time in any event of a galaxy, of a supernova, whatever, should be expanded when it is observed at low redshift by a factor 1 plus sect. For instance, in the light curve of the supernova, the light curves are multiplied. The period is multiplied by a factor 1 plus sect with respect to the period at rest in the supernova. This is indeed observed for the supernova, However, statistically, it is not observed for quasars, this time dilation, and it is also not observed for gamma ray bursts. So we don't know the reason for that. We should observe that. There are other papers too. We talk about some inconsistencies with the unification model, which affect the Seyfert in general, not only the quasar. As you know, the unification model talks about that the Seyfert 1 objects and Seyfert 2 are the same kinds of objects, but with different inclination, with different orientation. Some analyses show that the neighboring galaxies and also the host galaxies in which these black holes are embedded are different in Seyfert 1 and Seyfert 2. Well, this is not my work. They also talk about the possible selection effects, and they say this is not a selection effect. That they say they control this thing. But the question is that the inclination itself for explaining the difference between Seyfert 1 and Seyfert 2 apparently is not enough. They need something else to explain the difference between the kinds of objects. And in general, maybe it's my fault, but I find some misunderstanding in which is the mechanism of triggering the activity of AGNs. I find a lot of information which is contradictory to each other. Some people is talking about the triggering is due to the major mergers. Other people, like your paper, for instance, have not found any sign of major mergers in the AGNs. Other people talk about star formation, but this is again other evidences. There is also some literature which points that the AGN is quenching the star formation. But in my opinion, still there is something here to debate, and it is not totally clear. But there were some examples, just to mention some of them. If you want to discuss or you have some idea of other problems, we can discuss about it. Now is all that I have to say. Yeah.
Very much for this interesting talk. Time for questions.
Yeah, the typical question is that you have shown the failure of some orthodox models to explain this. Is there any unorthodox view that can more or less unify all the problems? I mean, well, not unify. I mean, to put some logic in the behavior of the quasars. I mean, the whole idea that the quasars are expelled by galaxies is still supported by any?
No, not apparently not. Very few people support it. No, in general, for all these problems, as far as I know, there is no any single theory which explains everything. However, there are maybe some proposals to explain some different aspects of the problems. But I think nowadays there is not a single theory to explain all these problems. No.
Another question is, don't you think that it is more difficult to understand the very big black holes in the very early universe than to explain that they are not active anymore now? I mean, nowadays we are happy with having extremely big black holes at the early universe with very active, but I think that is more difficult to understand than saying that the black holes are...
the lifetime of the black holes being active is quite...
But forming big black holes at the very early universe.
This is what I mentioned before, exactly. This is something that I don't understand, why they are forming. I don't know whether... I have seen some models, some papers in which they talk some models of formation of black holes, but they are very rough in the explanation of the details. I think they don't give an accurate explanation of all these problems. Yes, and also there were also some other theoreticians. It is not my field, but they have expressed some doubts about for the formation of very big black holes. You should have some other relativistic effects in the formation because the gravity is so strong for these black holes that you should have some effects which in some sense should not be there. But from the theoretical point of view, I think there are some things which are not totally clear, but I'm not a specialist on that. I can give you some reference of some people who have expressed some doubts on these kinds of objects, if they can survive or not. But from the point of view of simulations, and that I think there is some work, and people is happy with that.
No other questions? Yes?
It's about one of these works that is not yours, but you mentioned that the size of the clouds that you can detect as absorption features in quasar spectra is not the same. So these are clouds.
Not the size, the amount of structure, so the density of clouds.
But these are clouds associated with the quasars, or
no, the absorption lines of the quasars.
So, but these are clamps that are next to the quasars?
Normally people interpret the absorption lines in front of quasars with different redshift of quasars. They interpret it as clouds.
Yeah, but that's, okay. This is this problem is a property of the gas of the cosmic web, so to say,
yes.
Or the gas that is next to the quasars. So
next to the quasar, but not in the quasar, of course. It's surrounding of the quasar.
Okay, and so what's the problem? Could you?
The problem now is that the density here, the amount of the density of clouds, the amount of is different than the density here. In the radial direction, you have different properties than in the tangential direction. Are close to the quasar, not associated, not the quasar is the galaxy, the host galaxy, but around the host galaxy you have some structure, the Lyman alpha or whatever, no? I don't remember. I can show you, but they are in the same redshift, maybe a difference of 0.01, 0.02 of redshift with respect to the quasar. So it should be in the same system. Kiloparsec scales, possibly, yes, or maybe megaparsec also. Maybe reach megaparsec. Maybe the distance between Andromeda and Milky Way or what's it. No, here I'm not talking about jets. But here, no, do not confuse. In the previous work, I was talking about the jets, the superluminal motions and jets. Here, I'm talking about quasars. Most of the quasars do not present strong jets, so not all the quasars present jets and superluminal motion. This is something different. Forget about the question of jets here. Yes, yes, of course. But the question is why there is not an isotropy. You should observe the same thing in the tangential direction than in the radial direction, because the line of sight joining the quasar with us is not a privileged direction. Why there should be something in our line of sight? There is nothing to expect.
It's not the same whether the clouds are in the plane of the in the direction perpendicular to the plane of the galaxy, that if the clouds are in the plane of the galaxy. So I would expect that if the clouds are associated with the galaxy, that holds the equation. Of course, I should expect that some sort of
well, the clouds are, you can imagine that they are neighboring galaxies. It's like dwarf galaxies around. They are independent systems. They are not belonging to the galaxy. They are close. Maybe they are linked gravitationally, I don't know. But they are not in the same galaxy. They are not part of the galaxy. And in any case, I don't understand your argument because
you think that these are clouds?
you as an observer you should observe all kinds of combinations. Maybe you can observe the plane of the galaxy in the tangential direction, but sometimes the plane of the galaxy should be in the line of sight too. So statistically, you should not observe any preference for any direction. Statistically, for one single object, yes, but when you do statistics with many pairs of quasars, you should observe no preferent direction. All directions should be equivalent. As far as I see, maybe.
No, again, probably because I don't understand the problem, but so from the point of view of an observer in the galaxy that holds the quasar, the properties of the clumps of gas are not going to be isotropically distributed. For instance, the gas that you will have in the direction perpendicular to the plane,
but this is for one
probably
galaxy.
Gas that is going out of the galaxy.
Yes, but
whereas the gas you find in the plane of the galaxy is probably large-scale gas coming from the cosmic web, and so the properties are not going to be isotropic.
Yeah, but for one galaxy, yes, but when you observe many galaxies, the planes should be randomly distributed. So you mean that there is a selection effect? In this case, you are talking about some selection effect, like the jets. So you mean that we are observing this quasar because it is amplified by some jet mechanism, and this is the explanation that you are proposing. But this is possible for the jets. But remember that for only I think less than 10% of the quasars are radio galaxies with jet emission. Most of the quasars do not present such strong emissions of jets that I have shown before with the superluminal motion. So the emission of the quasar should be isotropic, as you have said. And if it is isotropic, there is no any preferent direction to. You should observe the quasar from any side, from the plane, from the pole position. No. Well, this is yeah, of course. You have this is the explanation for the safer one and safer two. If you observe here, safer one, if not safer two. But let's imagine that, as you say, imagine that we are observing the quasar face on, the host galaxy is face on. Then how can you explain the difference between the radial direction? Well, of course, the tangential direction you mean is in the plane of the galaxy. You mean that the tangential direction is in the plane of the galaxy? Possibly, yes. If there is an important selection of possibly, yes, maybe something. If this distinction is strong enough to produce a selection effect that you only observe quasars which with a host galaxy which is face on.
Okay, I think we can leave the discussion here. So let's thank Martin again.